Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Today I'm joined by Ahmed Saeed, who will be telling us everything we need to know about resource-efficient federated learning. Ahmed is an assistant professor at the Queen Mary University of London. Welcome to the show, Ahmed.
Yeah, hi, Jack. Thanks for inviting me, and I'm very happy to be within your podcast today.
Fantastic. So I've given you a very brief introduction there, but maybe you can tell us more about yourself and how you became interested in systems research.
Yeah, so again, my name is Ahmed Saeed. I'm assistant professor at Queen Mary University of London, and I lead the Saeed Systems Research Group, where we focus on scalable, adaptive, yet efficient distributed systems, and hence the name of the group. In terms of how I became interested in system research, actually, it is kind of early on during my undergrad. I have been, fascinated about, computer systems and their architectures. Actually, also more on the distributed systems and computer networks. And basically, my final year project was something around these topics, and we built communication systems back then to enable communication over the internet through Bluetooth. So back in the time, it was kind of there's no Wi-Fi. We had only Bluetooth. So, but in terms of building systems, it's kind of fascinating. I was fascinated by this because it's kind of challenging and also rewarding. So I think the various system components and protocols that keep our applications alive or every day's application that you use is very essential, and there's something interesting to look into how to make them efficient and scalable as the scale of our applications increase over the days.
As you mentioned Bluetooth, I remember being at school and it's like sending like music videos or music between us using Bluetooth with our phones and stuff. Yeah, that's and then before that it was infrared as well. We used to use.
Yes.
So,
yeah. Yeah, these are golden age. Kind of you had that very challenging task of sending even like short music that takes a while, and you want to make sure the connection is not lost, and you need it to stay together.
Yeah, we'd be stood there all lunchtime just to send like a 30-second clip to each other. Yeah,
but... Exactly. Yeah.
Cool, great. So yeah, today we're going to be talking about resource-efficient federated learning. So maybe you can just start us off by explaining what federated learning is.
Right. So in a nutshell, REFL has actually emerged recently. I mean, the idea of federation is not kind of new. There are federated databases, and it has been there for a while. But for machine learning, it emerged as a kind of a paradigm for allowing distributed machine learning. And it emerged as a way to address the communication issues initially. So it was introduced by Google. They had distributed learning that existed, but they weren't communication efficient. So they came up with this federated average protocol. And then this federated learning has also started to kick off and become very popular after they were introduced by Google paper, because now the privacy restrictions and regulations have been put in place over the past few years, and they are they had this limitation of how to train their models on the client's data while there is these privacy restrictions. So they came up with this model where instead of collecting your data into their servers and risking all the lawsuits about leakage or of their data, of the client's data or user's data, then instead now they ship the model or the compute to you, and the data stays within your device for training their models, and they just send some updates or based on these trained model locally. So it's kind of the interest of it has blown away over the past few years, and it's one of the highly researched area nowadays. And its main use cases to enable privacy preserving machine learning on users' decentralized data.
Awesome, yeah. So you're kind of pushing the compute to the data there rather than pulling it all in and then doing your computation locally. Cool. So yeah. You touched on a little bit there, kind of some examples of where FL is used today. So is there any other sort of, can you maybe give us some more examples of companies or applications that are using federated learning today in production?
Yeah, that's a good question, actually. So in federated learning, there is actually two different settings. We have the cross device, which is the most typical setting where you have, service providers, and these are relying on, user data from their mobile devices or smartware, all these kind of, or IoT devices. So you have large number of devices that have data and you want to train on them. So, for example, in this case, I would mention Google is using this to train their Google keyboard, and they actually highlighted that they improved the model by training on users' data instead of the held out data set in their servers. They improved their model by 24%, which actually kind of significant for them. Also, they use it for their Google Assistant, so to train their voice recognition task for the Google Assistant. Also, Apple uses this as well in their, Siri. Siri's voice recognition is trained by using federated learning on data from the users. So these are kind of examples that I can, mention in terms of cross-device. So another model is actually more related to organizations or companies, which is cross-silo. They call it cross-silo federated learning. And in cross-silo, you have organizations, and each organization can be, let's say, hospitals or banks or companies, and each of them, they want to collaborate on, training a global model that is kind of collaborative model that is more performant than their own local model. Because usually, for example, in hospital data, the medical images of users are quite private, and they are not allowed to share these data. So they use federated learning to train their models, for example, to do CT scan or whatever to detect certain diseases. And actually, there was a recent publication in Nature Communications that have gained quite some interest and citations, where there was a large-scale REFL deployment for tumor detection task among medical institutions and hospitals over 71 cities, crossing 6 continents. Typically, this wouldn't be possible without this concept of federated learning, because normally data are not allowed to be shared, and when they deployed it, they actually trained very good models, and it led to actually discovery of rare cancer that didn't exist. So they used it to in a kind of rare cancer boundary detection task, and they achieved quite good results. Another example would be also IBM. Also, research has recently announced a solution for money laundering or fighting money laundering, and they call this solution a private vertical FL for anti-money laundering. And I think these emerging solutions are quite nice and promotes more federated learning in practice.
Yeah, it really demonstrates the power of federated learning there. I mean, I guess the ability to kind of go across political boundaries and like different continents and everything, and kind of having access to all that, and like, yeah, fascinating. And I guess the numbers kind of speak for itself, and like 24% increases. Yeah, exactly. It's not negligible, right? So, and yeah, finding things like rare tumors, awesome. Cool. So let's go into the details of like how federated learning works a little bit more. So can you maybe walk us through the life cycle of how I go about kind of training an FL model?
Mm-hmm. Right. This is actually a good question, and it's important for the audience to understand the process. So let's say I'm going to use now actually the cross-device setting, because it's the more common setting, and that's where FL emerged from. So in the life cycle for federated learning, first you want to train the model and in a federated learning setting, and then the trained model is deployed for inference later on the target devices, right? So the main focus of federated learning is on the training cycle, actually. So in federated learning, there is the server or the service provider who owns a model that is designed for a certain task. Let's say the task is voice recognition or next word prediction for Google Keyboard or whatever, okay? And so they have designed this model, and they want to train it on the user data, okay? So we think of the users as the clients who own their smartphones or smartwatches or whatever, and they have data that reside on these devices, right? So typically what happens is that, first the users check in with the server saying that I'm available for the training. And we say check in here, meaning that like a kind of a login process is based on the availability of the client. So usually Google doesn't train or involve users unless they are connected to a charger so that they don't drain their power and they are connected to Wi-Fi and they are idle, not used by the user. So that to not overload the device. Okay. So after these devices check in, you may have like actually millions of devices or thousands of them checking at any point, right? So now the server needs to select a subset of this. Usually the subset is not quite large because the aim actually is to train on a subset, because when you train on very large sample, you have this problem of large batch size that actually degrades the model performance. So, and it's hard to deal with. So they take a subsample with a target number of devices, let's say 100 or maybe 1,000 within one round. And after this selection stage, which can be based on maybe random sampling or other selection algorithm, depending on their application, they will send the task to the users. And when we say a task here, it consists of the model that they want to train, plus any configuration like the hyperparameters or whatever to this device. Okay, so they are sent over the network to the devices. Each device start training its model on its local data. And they train it for maybe a number of local epochs. Okay, when they finish the training, each device needs to upload the model update. Okay, so this is an updated model, or after fine-tuning it over the local data, and it's sent to the server, and then the server goes over an aggregation stage. Okay, so typically the server sets a deadline, maybe 10 minutes, waits for 10 minutes for the clients to finish, and after this 10 minutes starts aggregating. Okay. So some of these clients are able to finish in time because we here see the clients are heterogeneous in terms of computation and the network, the data size or the size of the data set they have. There are many factors that contribute to the heterogeneity, and therefore not all of them are able to finish and submit the update. So some of them become a struggler and are missed out from the aggregation. Then after the server collects these updates, it does kind of apply the federated average algorithm by aggregating these updates to create a new global model. And these rounds are repeated over and over until the global model reaches a certain objective or target accuracy. And by that point, the model is said to be trained and can be deployed for the users.
So as you were kind of running through them, because I'm going to ask you next kind of about what are the various challenges that come with federated learning. You kind of touched on a few of them there, but I guess the first thing when we were running through that life cycle there was kind of the requirement of often being needed to be connected to Wi-Fi and being idle, because otherwise, if you're on the move, like things could be dropping in and out. Like the resilience there to sort of the kind of the clients dropping in and out, I guess is kind of quite hard to deal with.
Yes.
Yeah, because then you end up with maybe lots of stragglers. I guess you kind of have that, in a lot of cases, prerequisite of like, the phone's going to be plugged in. We're going to do it between midnight and 6 a.m. when the user's probably not going to be on the phone.
Exactly.
So when I plug my iPhone in, and that's on the night, that's what they're doing, right? They're doing some federated learning, and it comes up and says,
exactly.
That's great. Cool.
Yeah.
So maybe we can dive into a little bit more, a few of the challenges and then kind of showcase your work.
Right. So one of the major challenges I mentioned is the heterogeneity, right? So we have various sources of heterogeneity. We have the data. Each client has his own data, and these data distributions vary significantly among all the devices. So we are dealing with non-ID data setup, which is harder to train a model on. We have also the device and network heterogeneity, because you're using iPhone, I'm using maybe Samsung. We have with different computational configuration and background load. So this varies, and what type of network I'm connected with, and its quality. So also we have the behavior heterogeneity, which you just mentioned, is related to the availability of the devices, right? So this is very significantly, and creates more problem, and in some cases can create like an concept drift, where you are training in the night for some time zone, which is a day time zone for others, then you are kind of biased, or the model keeps shifting between one to another. So these are quite, significant challenges that actually leads to the federated learning model not to be able to, until this point, to compete with a centralized trained model if you have all these data. Okay, so obviously a centralized model is going to be more performant, but actually now the application of centralized model is prohibited more and more because of these regulations. The other issues is actually also related to, so if we highlight actually the high level issues, we have the problems with efficiency and effectiveness. So efficiency here, meaning the system efficiency and how we efficiently use the system resources or the client resources to achieve the target. And the challenges under this is like the heterogeneity and what type of optimization algorithms, and whether we do are we doing multitask learning or personalized FL or meta learning. So now you have various factors that leads to or feeds into the challenge of how we can make it efficient and effective training, right? Another main issue, and actually one of the significant one, is the privacy and security. So even though we say that FL is proposed for privacy preserving, I mean, by itself, it doesn't have any privacy guarantees, okay? Because there are attacks that can still restore the data of the users, and they have been applied successfully. So there are further privacy enhancing techniques that have been proposed in the literature, and there are a wide, kind of research into this, like a differential privacy, homomorphic encryption, multi-party computation are some of these techniques that are being researched to enhance the privacy and security, right? And also you have also the malicious clients and actors and the adversarial servers, right? So these are more issues into the problem. Another big issue is, or if we categorize them as a big categories, the third one would be the fairness and bias. Okay, as I just mentioned, when you shift between time zones, you have fairness issues, right? Because the ones involved in the training are not representative of the global population, right? So there's a fairness and bias issue. And the problem is how to leverage or introduce kind of diverse techniques that ensures high level of diversity. The last and also one of the major challenges that are not widely researched, there are a few research works that coming in, is the system challenges and how to make the system are platform and deployment friendly and easy to scale with a large number of users. Until now, I don't think there is a very large scale deployment other than the ones provided by a large scale providers like Google, because they have control over the the end device in some sense. So for other competitors, it's a bit hard to deploy this in scale. And also there are also the system parameters tuning, how to parameter various system artifacts, like the server side. There are many parameters that can control or affect the global model training, such as how many clients I select per round, how long should I wait, the reporting deadline, and there are so many things that play in and can affect the quality of the final model. So there are system research challenges here also as well. So globally, if we think about them, we have efficiency and effectiveness, we have privacy and security, we have fairness and bias, and we have system challenges. So I think these are the kind of four categories that I think of in terms of big picture for FL challenges.
It sounds a very fertile ground for research, and there's so many challenges to kind of get stuck into there. Cool. So you mentioned there that there's kind of been some of these challenges have kind of prevented FL getting near to like centralized sort of learning deployment at the moment. So you kind of mentioned in your paper that the key performance metric in FL is this time to accuracy. So can you maybe tell us kind of a little bit what this is, and then what the sort of main determinants are of achieving good time to accuracy?
Right. So many work actually now focus on this metric. They announce or pronounce it as time to accuracy, and they came up with this naming. So in simple words, this means how much time you needed in terms of runtime to achieve a certain or your target accuracy. So you remember one of the objectives is to train the model until it reaches a target accuracy, right? So now, if you think about if you use just rounds, it may not be easy to compare, because a round can take 1 hour or 1 minute, right? Okay, so to have a fair and practical comparison from the system point of view, we look at the time, because the time is kind of invariant. Because I mean, when I compare a time, it's kind of a common ground that I'm comparing everyone with, right? So they look at minimizing the amount of time needed to achieve the highest accuracy possible, or the target accuracy that we are aiming for. So that means the time to accuracy metric. This actually depends on two factors. One of them is the statistical efficiency of your training. So statistical efficiency means by how much your model has improved within each round, right? Okay, so we are looking here at the quality improvement or the accuracy improvement, the deltas in accuracy. So this is the statistical efficiency of the training. So if you have more statistically efficient kind of algorithms, then your model will go to the target accuracy faster, right? I mean, in terms, because of the delta is higher, so you reach the target faster. The other way, in looking into the time, is the system efficiency. How efficient is your system? So, and it usually refers to how much each round takes you to finish. And this depends on the various system factors in terms of how fast the training is moving on and how long training takes. And this can be depend on the computation of the end devices. So some work actually just select the very fast devices to participate, or they also apply some compression techniques to reduce the communication time. They apply many techniques to reduce the length of the round so that you achieve the target faster.
Yeah, on the statistical efficiency, I guess you get like marginal gains the more rounds you do, though, depending on what approach you use, right? But I guess like not all rounds are equal, is what I'm trying to say, right? So like
exactly,
you have to factor that into, because maybe the 10th round you're only getting an incremental gain of like 1% or something, right? And so I guess that has to play into it as well.
So yeah, that's correct. Typically, at the beginning of the training, actually, your margins are higher than the later stages of the training. So you see larger improvements at the beginning, then the model starts to saturate, because maybe it doesn't learn more, or you are not changing the learning rate. There are your learning rate schedule, whatever. So there are factors like related to the learning task itself, what kind of optimizer, the aggregation process, how many learners you are aggregating, the mini batch size. There are so many factors that play into this statistical efficiency.
Cool, yeah. And the kind of another thing that jumped out to me when you were talking about system efficiency was kind of that sometimes like people just select the fast devices. But do you get any sort of biases implicit with selecting certain devices and the speed of them? Because like even the user data on them may be different, right? So there's maybe or does it kind of not matter? I don't know.
Yeah, so this is actually one of the main motivation for our work in REFL. Actually, we looked at the works that aim to optimize the system efficiency only without thinking about diversity, and thought about this is not right, because you are kind of biased in a sense. You are not improving anymore when you are keep training on the fast devices, and you are leaving out strugglers or slow devices that they may have valuable data. Okay, so maybe these fast devices, they have only a subset of the classes, and you are not seeing the other classes that are of interest from the slower devices. So kind of this bias is actually problematic, and that was the main trade-off that we looked into in REFL. We have the system efficiency versus diversity trade-off, right?
Okay, nice. Yeah, because you mentioned in the paper that you kind of optimize design for this before you call it resource to accuracy instead. So
yes.
Is it like, can you explain like kind of what? Well, I mean, maybe we've just touched on it there, but can you maybe go into that in a little bit more depth, and like I know you maybe said why you did it.
Right. So in the paper we use a different metric, and instead of looking at just a time, because it may not be the right metric. So in fact, in some cases you want to optimize how much resources, because if you think about these users, they are kind of resources that you are leveraging and using, okay? And it's not free resource, right? It's not owned by the service provider. It's not your resource. So typically you would like to reduce the resource consumption of these devices, as well as reducing the time. So it's by ignoring the consumption on these devices is not kind of sustainable solution. Typically, if you are going to consume many resources that I paid for as a mobile user, and on my smartphone you keep consuming my resources for your REFL, then I actually wouldn't be willing to participate in this and may actually opt out, right? Because you are harming my device, you are deteriorating its performance, et cetera, right? So we looked at the computational resources that are needed, the total, in terms of how much compute and communication time that you are using to achieve the target accuracy. And this actually can extend to this situations where you are training on battery-powered devices instead of like Google's assumption that you need to connect it to a charger. Then it's very important now, if you are training on battery-powered devices, to reduce the consumption on these devices in terms of compute and time. So it extends more on a wider applications and scenarios instead of just focusing on time to accuracy.
Yeah, cool. I was just maybe going on a tangent a little bit here about the opt-in, opt-out sort of thing here. So like when, as an end user, obviously because the companies are doing this, like Google are doing this, like you said, with the keyboard. When do I opt into this? Is it like, do I only kind of download the app and whatever, and you just sign? You click terms and conditions, accept. Am I just signing my life away there?
Well, usually there is a kind of a banner that appears, usually saying that would you like to be part of the analytics, their own analytics, right? I think these are the kind of when you opt in and actually you can later opt out if you opted in initially. So I think in many cases people doesn't realize that this is happening because it happens in the background and while the device is idle. So that's why they do it for purposefully when the device is idle, so that you don't realize. But still, they are using your resources, right? I mean, this is something, a resource you paid money for, and they are consuming it for their benefit.
Yeah, that's probably why the battery life on my iPhone sucks. But yeah, anyway, cool. Let's dig into REFL some more then. So maybe you can give us a high level overview of how it works and talk us about the architecture of REFL.
Yeah, so basically, as we have said, the main pitch for REFL was that heterogeneity is one of the major challenges, right? As I explained, and it's obvious now. And we find, as we said, the state-of-the-art work addresses heterogeneity in a way that introduces a trade-off between system efficiency and the resource diversity also, right? And also we found that these solutions doesn't have, the resource consumption in their mind, and they never, thought about how much resources I'm consuming to reach this. They care about minimizing the time from the point of view of the provider, the service provider, because the provider wants to train the model fast, to deploy it fast, right? They never thought or took the point of view of the client side and the resources consumed by the client. And that was the main thinking within REFL. Okay, so we thought about how we can build actually a practical solution that still achieves, the time, good time to accuracy metric, while also, reducing the resource to accuracy metric. So and that's why we came with this resource efficient federated learning system. So if we dig deep into the main components of REFL, there are two main components. Okay, so one of them is the intelligent participant selection component. Okay, or we call it IPS, and this component aims to increase or improve the diversity of the training. Okay, so typically, as I said before, some works like ORT that we was one of the state-of-the-art that we compared with, they rely on a kind of biasing the selection toward the fast clients. And it wasn't ORT only. I mean, there are other works that did this in terms of improving the time to accuracy. Okay. However, we found that this is actually harms and is not useful in the non-ID setting, and the model qualities are not good as claimed. So we thought about how to overcome this issue, and we looked at the availability as one of the factors that have never been used as a kind of ways to tune the training. So we have clients that are not always available, right? So, and if we want to diversify our training, we should care about or consider how long they will stay for the training, right? And rationally, you would normally prioritize your selection towards the ones that you know or likely would be not available in the future. Okay, so that you can capture their data in your training, and then if they leave out the training and never come back, you still they contributed to your model, right? So to do this, actually, we needed to introduce actually a availability prediction module on the devices. Okay, so this is kind of a very simple time series prediction module that runs on each device. It's not on the server to avoid any privacy issues. It runs locally on the device, and it trains on the device patterns. So it looks at the patterns of your use of the device and your charging and stuff like that. So we focused on the charging state as kind of prediction of your availability, because we assume that you will train when you are connected to a charger. So, and this module will tell us kind of with how, for each next round, okay, if you are online, it will tell us if you're going to be online for the next round or not, okay? And this will be sent as a probability value to the server, and the server gets these values from the clients and selects the least ones as the candidate for this round, because they are not likely to be available then in the next round, right? So that's how we done the intelligent participant selection module. And this eventually will improve your diversity of the clients and improve the model quality, especially in the non-ID setting that is the typical setting in Federated. So we have actually another module called staleness aware aggregation. So we talked about struggler, right? So some clients are, can struggle, and usually in Federated average, these clients are left out. When you have the deadline, reporting deadline, if these struggles don't come in time, they are left out from the aggregation. Okay, so it's like kind of, you think about it as kind of wasted resource, right? So these clients have already, spent some time training, right? And because they were unfortunate to not have a very fast device like others, or their network got disconnected or whatever happened, right? Because you don't see what's happening on their side, they were left out. Okay, so normally these updates are lost. So it's wasted resource, right? So we introduced a stale aggregation rule. In a sense, we allow these clients to submit their updates even at later rounds. Okay. However, the problem with this is that when you aggregate these stale updates, it will degrade your model quality, because your model already shifted from this model that they start training on, and they moved on to a different model. Okay, so let's say you're at around X and they submit at round X plus 10 rounds later. The model already has changed, right? So you have fresh updates from the clients that are training on that updated model at X plus 10, and you have these stale with the model that is in past by 10 rounds. Okay, so we introduced some rules to actually have a better effectiveness or efficiency from this stale aggregation. And this rule involves two factors. One of them is the dampening factor, which try to dampen the effect of this stale update. So when we aggregate, okay, there are weights that is applied or multiplied by the model update, so that it doesn't have the same impact as the fresh models. Okay, so we have dampening factor that depends on how stale you are, right? So the more stale in the training you are, or the model are, then it's damped more in terms of its effect. And we have another factor called boosting factor. We actually boost your stale update by some value based on how deviant you are from the fresh updates. Okay, so if you are different, meaning that you have new knowledge or something new to contribute. Okay, in a sense, we look at this is a client that had maybe different data, and that this will contribute something new to the model. So we give you a higher kind of weight, and we have the weighted sum between the dampening and boosting factor to combine them in a single weight that is applied on the stale updates. And actually, we experimented with this and had like a kind of convergence analysis, and we did ablation study until it was hard to reach the best rule for this. And the ones who are using the paper, actually, we found it leads to better accuracy for the model.
Yeah, I have a quick question on the how you measure that some stale updates going to be beneficial, or how do you measure its difference from like it's got something good to contribute and boost it up? How do you measure that?
Right. So we have the fresh updates, right, or the fresh model updates. We average them, right? So and we have this stale update. So we apply a kind of a KL divergence metric to look at their divergence, and also we tried other functions like cosine similarity and these kind of functions that's used to find the distance between two objects, and we use that as a way to look into how deviant you are from the fresh updates.
Okay, cool, that makes sense.
More details actually are in the paper. It's hard to explain this in a podcast. A kind of or virtually, basically.
This is true, yeah. So the interested listeners should go and check out the paper,
yes,
for sure. Cool. So let's talk some numbers then. So can you tell us about your experiments and how IPS and staleness aware aggregation actually performed in practice?
Yeah, that's a good one. So in our experiments, actually, we used the NVIDIA GPUs clusters to train our model. So we train in a simulated environment. We actually didn't train on end devices because it's hard to train this in the wild. So what we do is emulate the client's training on the GPUs, like a V100 or A100 GPUs. And we simulate the training effects, like the client selection, the aggregation, everything is kind of simulated and the runtime. And we used actually realistic computational profiles for the devices, like there's AI benchmark that is profiles various devices and gives you the actual runtime for inference and training on these devices. And there's also MobiBerf trace that has traces of network speeds from over the globe, and we use this to profile devices. For heterogeneity, also there is a trace that we have used for emulating the availability of the devices. So in total, also we each experiment we repeated it 3 times and I took the average of this, and this actually amounted for almost 13,000 GPU hours of training, which is significant. So if I talk about numbers in terms of comparing with the state of the art, when we compare with ORT, right? If we run for long term, a number of rounds until the convergence, we see that REFL achieves a model that is higher in accuracy compared to ORT by 20 points. Okay. So this is actually a significant number. I mean, if we talk about numbers, REFL achieves 60% accuracy, while ORT at that point achieves only 40%. Okay, within the same resources, right? If we talk about the amount of resources to achieve to accuracy. Okay, and also REFL also managed to achieve this within reasonable time, even lower time than ORT. Okay, compared to another state of the art, which is SAFA. SAFA is a kind of a different algorithm that kind of allows for diversity and stale aggregation by not even having a selection. In SAFA, there is no selection; everyone is selected, right? So the problem with SAFA is that resource wastage is high because you are selecting everyone, and then when you do stale updates, you have a threshold. Like you say that by default they use 5 rounds. Anything that is beyond 5 rounds is discarded. So again, there's a problem here of resource wastage. So we found when we compare with SAFA to achieve the same target accuracy, let's say 50% accuracy on the Google Speech benchmark, we achieve more than 2x reduction in terms of resource usage, okay, which is significant at the same time. I mean, even the time didn't vary much. I mean, we took 12 hours, they took 10 hours, which is not quite different in terms of runtime. But the reduction in resource usage is quite significant. And if we look at larger scale experiment, we did even larger scale experiments compared to SAVA. When we have 3x number of clients, the reduction is more than 5x. So when you go larger and larger scale, you're gonna gain more in terms of reduction in terms of resource usage. Also, we looked at the future-proofness of REFL, and we found that it's future-proof compared to ORT or other mechanisms that are similar to ORT. And in this experiment, we looked at doubling the computational speed of the devices. Okay, So we took like different percentages of the population, of the device population, and doubled their speed. So we took like 25% doubling their speed, 50% doubling their speed, because the speed of devices improve over time, right? So in the future they improve. And also we looked at 100%, all of them doubling the speed. And what we found is that while REFL and ORT gain from both both of them gain by reducing the time and the resource consumption by this doubling of the speed. In fact, the problem with ORT is the quality doesn't improve. I mean, it's still the quality stays the same because it's biased. They select only the fast device. You give more fast device, they will only target these fast device. And REFL, no, we have diverse selection, and that's why the results of accuracy keeps improving by doubling these speeds.
Yes, on that really quick. So when you double the speed, did you also then increase the variance of you still have the really slow old devices, but then you've got some devices that are now twice as fast, or was it just the kind of the average speed that increased?
No, there is still this variance. I mean, the old devices, they maintain their own speed, only 25% just doubled.
Okay, that makes sense. So because you can imagine a future where, I guess I don't know if this is true, but does I'd expect the variance in devices to probably increase over time. Maybe I don't know. I'm just kind of shooting from the hip there.
I guess if you think about it, some devices, their improvements are significant compared to others. Usually, it's not uniform. The improvements by companies and devices because of the hardware configurations, setup are different from company to company.
Yeah, because I guess kind of not many people now are using an iPhone 3G, right? They're kind of all gone off the market, right? So, yeah.
I guess, that's right.
There's probably a lower bound in kind of the version that people are running on phones. People are running on. But anyway, cool.
Yeah.
So it sounds an absolute win on all fronts. Does REFL? So let's look at it from the other side for a moment. Kind of what are the limitations of REFL?
So REFL, like any other federated learning system, have a common limitations, and one of the key limitations is actually dealing with misinformation when you have malicious or non-faithful clients, right? Because if you think about it, we are relying on a prediction model that is trained on the device, right, for predicting the future availability. So imagine the situation that these clients are, sending wrong information. So actually, we dealt somehow with this in REFL by, prohibiting a client that were selected for one round to participate for 5 rounds in the future. So in some sense, if you lie about your future availability and say, I'm not going to be available in the next round, and you were selected, this will not help you to be selected in the next 5 rounds because you were selected for this round, in some sense. But I think this misinformation, because you're dealing with clients that exist in the wild, and you don't know, and there's communication channels that exist. This problem of misinformation is actually quite challenging to deal with. Okay, so this simple solution may not actually be the best solution, but this is one of the limitations that exist. The other limitation that we have so far is actually how to automate the fine-tuning of the various knobs that we have in this system. And this also not just REFL. Most REFL systems, they have this problem, because you have a tremendous number of factors that play in, and hyperparameters at the server side, at the client side, and the optimization algorithm and the learning process. The multitude of these knobs that you need to tune is very hard compared to training on a centralized setting. So I think these are the main limitations that exist, not just for REFL, for other systems as well.
Cool. So with those in mind, what's next on the research agenda for REFL?
Well, at this point, actually, we are thinking of expanding REFL, because REFL is limited to only federated learning setting, right? We actually thinking about expanding it to be a major framework that can support various techniques or distributed learning techniques, such as transfer learning, multitask learning, personalized REFL, and decentralized learning kind of techniques. And I think it's I mean, until now there is no such framework that are kind of inclusive of all these techniques. Mainly they are federated learning, and there are other small works on transfer learning, and there is no major framework that capture all of these. And I think this is beneficial because it's good to have some kind of a generic and inclusive framework of various techniques, because in some cases you can have transfer learning based on federated learning, right? There are some work on transfer federated learning, and multitask learning can be applied in also federated learning. So it's good to have a framework that have these kind of techniques.
So yeah, so my next question is kind of, as a software developer, data engineer, how do you think I can leverage the findings in your research, and what impact do you think this can have longer term?
Yeah, actually, this is a hard one, but one thing that I can say actually is that still the current REFL systems are not there yet. I mean, there are many frameworks that are coming into picture, and they are evolving over the past few years. Like there are Flower, there are FedML, FedScale, and FedAI. There are various frameworks that are coming from several startups, and I think they are evolving over time. But I think as a system, we are not there yet. I mean, there are so many challenges and solutions that make REFL kind of practical for wide deployment. And also we have the barrier of large companies or providers having control over the end device, which actually make this deployment even harder. But I think the results we have obtained in REFL actually we think is quite a major step that can towards having a resource efficient federated learning, because we took the view of the client side in terms of the resources they use. And when you say to the clients, I have a resource efficient system for training, I'm not going to impact you much in terms of the training, and eventually the training model will be beneficial to you, I think more users will be willing to opt in, right? So I think it's one good step towards the adoption of thinking about resource efficiency and building more robust models in a sustainable way over decentralized data.
Fantastic. So when you've been, how long have you been working on REFL for? How long was the project?
Well, I think we started at early 2020.
Okay. Yeah. Just before COVID.
Yeah, exactly. I think we started by that time. I mean, my work started with distributed ML in a context of HPC and clusters. And then we found more problems in federated learning that are interesting and worth looking into and solving. And that's why we started working on it. And I think it took, I mean, more than 2 years to come up with the complete framework and all the experiments, because you see the experiments took quite significant amount of time, and we tried to look at all aspects for evaluating it.
Yes, so kind of across that period then, what's the most like interesting and maybe unexpected lesson that you learned while working on it?
Well,
caught you off guard, yeah.
Yeah. Well, I think system research actually is quite hard. I guess this is my experience. Is very hard work. It takes some time and persistence, and it involves many sleepless nights and bashing your head, scratching your head, and stuff like that over bugs that you don't know what's happening, and it's because so many things are in play, and sometimes you get non-meaningful results, and you need to find where exactly where is this coming from. But I think the ultimate reward is actually quite high compared to other work, because you see your work in practice. It's kind of a living creature, something that people can relate to or feel, basically, right? Compared to other kind of, I'm not saying low on the mathematical or theoretical work. They are important as foundations, but you don't feel it, right? I mean, and I think It's also the open sourcing and making your solutions kind of available for others to use and practice. It gives you some joy and kind of achievement in terms of you contributed something to the research and the community as well, to other researchers and community as well. So I think the lesson learned from REFL, it was hard journey, but I think now if it is something that can be beneficial in the future in terms of systems that uses its concepts or algorithms to make their systems more resource efficient, this is something that will give us significant joy.
Yeah. Do you have any? So, what other research have you kind of got going on at the minute? Or is REFL sort of your main vehicle for research at the moment?
Well, so it's not actually just REFL. I mean, we have other kind of work that's going on, but I think the main theme that we are focusing is still federated learning. We are looking at other directions such as battery-powered scenarios, how to leverage techniques, as I said before, transfer learning or knowledge transfer. So we are looking into still the main theme of the big picture of federated learning, but it's kind of the main theme that I'm focusing on now, yes. But there are other works. In terms of computer networks and the civil systems, there are other works that I'm interested in, but the major driver, as you say, is federated learning.
Cool. Yeah, got many irons in the fire then. Cool. So how do you go about so this is my favorite question. I love this question. How do you go about generating ideas and then selecting which things to work on? I kind of want to know more about your creative process.
Yeah, so I think this is actually quite tough one. I don't think there's a single, a universal approach, and there is no right approach, to be honest. But I think we usually aim to first identify the problem based on the recent line of work, right, and see how the state of the art have achieved, and so that we know this is the point we need to start from, right? And we try to critically analyze these, state-of-the-art solutions by, trying to maybe experimenting with them or analyzing their model or the solution they are proposing. Is it practical? Is it efficient? We look at all these, aspects and dissect these solutions to find exactly what they have missed or overlooked in their solution. And before we make any claims, we try to quantify their limitations by doing experiments so that we can motivate our research area or question that we are, we're going to investigate further. And then after this, after you are defining your research question, you have a project. Then, developing the solution, I think it's kind of folds naturally by, thinking about various algorithms and techniques that can work out with the the final objective that you have identified in mind.
Nice. That's another good answer to that question. Like I said, I love that question. It's great to see how everyone works and approaches this thing. It's cool.
Yeah, I agree with it. It's a tough one, and I don't think my answer may be the optimal or the best one, but I think everyone has his own approach, and I think if it's working for you, then you go for it.
Exactly. Yeah, there's not a one size fits all sort of approach to that thing, right? You've got to find what works for you. That's the thing. Great stuff.
Exactly.
Cool. So I've just got two more questions now, and the penultimate one is: what do you think? It's a very big picture. What do you think is the biggest challenge in kind of systems research, federated learning today?
Well, I think first and foremost is actually the main challenge for us in this research area is actually finding skilled and motivated researchers that work on system research. Okay. And finding the ones with the right background and experience is extremely hard because you are competing in academia, you are competing with industry that pays quite well, and it's very unfair kind of competition for us. It's very hard to find good researchers, especially in system research. And the second issue is actually with our research is to have enough time and perseverance and right resources, because eventually you need the hardware resources to run all of these, and you need time and persistent. So I think these are kind of challenges in terms of personal challenges to adapt yourself, that it takes time. You don't want to just rush things. You need to study carefully the system and run experiments accurately to get the correct results. So I think these are the two biggest challenges: finding the right researchers with the background in system research is very hard. The other challenge is having this personality or adapting yourself to the nature of system research. It's not the typical research that you just build a model and run it on MATLAB and get some results and publish it, right? It's different, totally different kind of research, and that requires time, resources, and perseverance.
Yeah, that's nice. Cool. So last question now. What's the one takeaway you want the listener to get from this podcast today?
Well, again, I'm going to reiterate now on that. System research is quite painful. I mean, if you are doing it, I salute you. But it's fun. I can say it's fun because it allows you to acquire multitude of skills and experiences, and actually makes you more I think eventually when you are coming out of systems research, your opportunities actually in the market is higher, because it's kind of unique and rare kind of resource and skill. So it's something that is going to be rewarding eventually, if you don't work in academia. Like myself. The second thing is that I would like is that the outcomes, when you have outcomes like papers or open source code, these usually that comes from system research have higher impact than other type of work, because these can be adopted by systems used in big companies or providers. And most, actually, if you think about it, most of the great systems like Hadoop, Spark, all these systems actually came out as a result of a system research within these companies. So if you think about it, most of our systems that exist today actually is a result of system research. So I think this is the main message, that system research is actually quite great, and I hope we can find more people doing it.
Fantastic, great. Let's finish it there. Thanks so much, Ahmed, for coming on the show.
Thanks,
if
Jack.
Listeners interested in knowing more about your work, we'll put links to everything in the show notes. And if you enjoy the show, please consider supporting the podcast through Buy Me a Coffee. And we will see you all next time for some more awesome computer science research.